We'll get started. So today we are very happy to have Professor Long Ju from MIT giving our colloquium. Long got his bachelor degree from Tsinghua University. Then he actually came here, did his PhD in my group. He has done many kind of interesting work as a PhD student. And studied the combined like electrical and optical characterization of the materials in my group. And afterwards, he was heavily postdoc at Cornell with Paul McEwen. Then he became assistant professor at MIT. Long has done many creative work, both in optical spectroscopy as well as electrical transport. Notably, he discovered this fractional quantum anomalous Hall effect, also signature of chiral superconductivity in crystalline multilayer graphene, and that's what he will tell us today.
So yeah, okay, thanks, Phil. I thought there was a convention of 5 minutes behind the the starting time. Colloquium now, okay, fine. Okay, I'm very glad to come back to Berkeley. And I left about like 9 years ago, slightly less than 10 years ago. But as you will see from my talk, I'm still doing works that's kind of, that I got enlightened when I was at Berkeley. So I'm going to tell you about emergent quantum phenomena in crystalline multilayer graphene. Okay, this is part of graphite. There's no twisting. And I hope I can convince you that even in 2024, 2 decades after the first isolation of monolayer graphene, we just don't understand it's a very simple, both structurally and chemically material. Before I get started, I'd like to acknowledge the people who contribute to the work I'm going to tell you about. These are my students at MIT, and Zheng Guang was a postdoc in my group. Now he's a faculty at Florida State University. We got the support from our theory friend, Liang Fu and Fan. And we got nice HBM crystals like everybody does from the NIMS in Japan. And I'm also going to touch a little bit on the work we did with Ray and Hong Kun. So we condensed matter physicists are interested in what can emerge from the setting of many identical particles of elementary particles, right? We're always dealing with a system that has many identical electrons, nuclei. We put them together in a setting called crystal. And we also know that in almost all the materials, there are a lot of defects and disorder. And however, sometimes we can measure phenomena that is amazingly robust, that's precisely quantized, due to some big guiding principles of physics, right? For example, when electrons pair up to the so-called Cooper pair, they can give us the phenomena as superconductivity, where they become very robust against scattering, and you have absolutely zero resistance. Another class of phenomena that is very robust and you can measure macroscopically, very precisely quantized number is the phenomenon in the topological class, right? For example, you can measure a Hall resistance that's determined by just h over e squared, fundamental constant, divided by integer number called Chern number here, right? So you can apply magnetic field to a 2-dimensional electron gas, and you get plateaus in the Hall resistance that's precisely quantized of 1 over the integer times h over e squared. So these phenomena are in the category of so-called emergent quantum phenomena. And they happen in many different types of materials and in very different experimental settings. However, if you ask what is essential to get such kind of phenomena, here's my view. Number one is that you want to look for some kind of flat electronic band to promote electron correlation. Because when the kinetic energy of electron is small, the interaction between them becomes important, and very likely you're going beyond the single particle physics, and some phenomena that could be promoted and happen. On the other hand, if you want to get topology, it has to do with this very fundamental concept called Barry curvature that was having effect on how electron moves in crystal. Okay? This is 1954, and at that time people already find that there's so-called anomalous velocity that's determined by the periodical part of the wave function in your block wave function. And if you integrate this Barry curvature for over a completely filled band in the boron zone, you're going to get this integer number, Chern number. Okay, so these are the essential ingredients, but as an experimentalist, I want to ask, in what material, system, or setting am I going to realize these conditions so I can possibly get emergent quantum phenomena? So we have this lore, we learn through the decades of condensed matter physics, okay? Which is, we should make some crystals. We throw atoms, like the 5 different type of atoms, into the furnace. We heat it up, and it will naturally, but due to chemistry, give us this very organized, highly ordered crystal structure, and something amazing could happen. For example, high TC superconductivity. Or we grow this kind of vertical heterostructures based on semiconductors, atomic crystal semiconductors, and we apply high magnetic field to quench the kinetic energy to form lambda levels, and we can also promote correlation and topological effect. And in recent years, there's a new platform to engineer correlation topology. And this is done by assembling atomically thin materials on top of each other. For example, graphene is a 2D semi-metal, and you can have 2D semiconductor, you have 2D magnet, you have 2D superconductors, and you have an unprecedented opportunity to assemble them back into a heterostructure where you can control the layer number, you can control the chemical species, and you can control the twisting angle between these layers. So you can you can invent material that was not allowed to happen when you throw atoms into furnace, and you hope the interactions between these adjacent layers is going to give you something that's absent from each of the ingredients. So something emergent from the interaction between these layers. And this is still in the 2-dimensional limit. So you can still play this trick of applying a battery voltage to control its charge density and sometimes the band structure, right? Especially in recent years, this concept of Moiré superlattice has been used a lot in such kind of van der Waals coupled 2D materials. And Moiré superlattice is some kind of spatial beating between 2 patterns. For example, between graphene and HBN, this is, I think this is one of Mike's early work to first tell people that such kind of large-scale spatial beating could happen when you have graphene on HBN, even at the 0-degree twisting angle, because there's a lattice mismatch, about 2%, between graphene and HBN. Of course, you can also play with the twisting angle between the layers to further control that periodicity. What you get eventually is that you can further control the band structure and the interaction energy scale when you put the electrons into such kind of additional periodical structure that's much bigger than the atomic lattice. So I was enlightened by both of these 2 types of wisdoms, okay? The first wisdom is chemistry is great. It gives us highly ordered structures, very robust, highly repeatable. However, it is hard to tune. Once you grow the crystal, you can hardly tune its properties through something called gate voltage. On the other hand, the stacks of 2-dimensional materials, especially with Moiré, is very rich in the structure, right? You can have unlimited kind of combinations of these 2D crystals, and that's what they can give you. However, it suffers from a type of disorder that you don't really get from crystals. Because there's no chemical bonding between layers, strain can easily build between the layers and distort the spatial structure that you wish to be uniform. For example, if you get two pieces of graphene and put them on top of each other close to this so-called magic angle, like my colleague Pablo did, you're going to get superconductivity. However, microscopically, there's a lot of twist angle variation due to this kind of inhomogeneity. So you're not really getting a homogeneous superconductor. Instead, you get a percolating network of supercurrent. And that's what you measure at a microscopic scale. So I was enlightened by the advantages of these two wisdoms, and I'm aware of their disadvantages. So what I want to do is to combine them. I want to find some two-dimensional material in the crystalline form already has flat band and some correlation effect. And then I'm going to introduce other layers at proximity. So I can dress the flat band in my 2D crystal with proximity effect. For example, spin-off coupling, or Moiré as a proximity effect to make things even more interesting. And hopefully, I can find a good combination of these two wisdoms to get highly tunable and interesting correlation and topological effect. The question is, what kind of 2D crystal I'm going to use as my building block? And the answer is graphene. Okay? So this is something I've been studying for 6 years when I was a PhD student here. I keep studying it. After I left as a postdoc, I'm still studying it as a faculty myself at MIT. And the reason is, it is a very rich system and highly tunable. So we can get a lot of things we wish to have for engineering correlation and topology. Specifically, I'm going to share with you 3 examples today where we realized the so-called integer quantum anomalous Hall effect in part of graphene, and the fractional version of that, still at the zero magnetic field, and finally, some chiral superconductivity. Okay? So let me first tell you, what do I mean by finding correlation in graphene? Isn't graphene already very well known and people are so bored with it, so they start to do some twisting to give it a twist? Well, if you use tape to exfoliate from graphite, you get this random thickness that you can tell from your optical microscope image. The optical contrast basically tells you the layer number of the carbons you have there. Okay, that's good. However, not many people appreciate that even within the region that has a homogeneous layer number, there could be subtleties about how the layers of carbon are stacked on top of each other. If you have monolayer graphene, it's always like this. If you have bilayer graphene, in the stable form, it's always a so-called A-B stacking. But if you go beyond 2 layers, get into 3 layers, you have to decide whether to shift the 3rd layer to the left or the right with respect to the first 2 layers. And that will give you these 2 different stacking order. One is known as Bernal stacking, and the other is known as the rhombohedral stacking. Bernal stacking is energetically the most favorable form of graphene stacking or graphite. You get a piece of graphite, about 80% of volume is going to be in Bernal stacking. Well, rhombohedral is less stable, but you still have probably like 10% of your graphite to be in this kind of stacking order. And you don't have to believe me that there are these different configurations within a seemingly homogeneous region. There are really ways that allow you to visualize them. For example, you can look at the Raman spectroscopy spectrum of different part of the flake. And if you look at the specific phonon peak, it's going to show different shape, and that tells you where is the ABA, or the Bernal stacking, and where's ABC, which is rhombohedral stacking, right? You can do mapping by scanning your laser. Or you can do what I did, like when I was still a student with Fan, we sort of borrowed this infrared SNOME technique, where we shine infrared light on a tip scanning over the graphene flake, and we collect the scatter light signal. Due to the different infrared conductivity, we can also tell the difference between ABA and ABC by scanning the tip across the flake. Okay? I was asking myself, given that there are different stacking domains inside exfoliated graphene, can I see them? what I mean by seeing them is not like spending hours or tens of minutes to scan something to point by point. I really want to see something like how your eyes works, right? And turns out that is possible. It's very simple. The trick is that instead of using visible light, which doesn't really show the different stacking orders within a layer number homogeneous region, you just increase the photon wavelengths that you use to somewhere in the near infrared range. In this case, about 1.7 micrometer, you can already see the difference between ABCA, which is rhombohedral, and ABAB, which is Bernal stacking. You can even see a third stacking order, which is ABCB in the 4 layer. This takes you less than a second, and you can readily differentiate the different stacking orders. So given that we have these different stacking order, why is it that interesting? The rhombohedral stacking is a very interesting configuration of carbon for the following reason. So in the rhombohedral stacking order, it goes as ABC, 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 right? And if you just draw, the unit cell, you grab 2 atoms from each layer, and you stack them on top of each other to form the staircase structure, eventually you're going to get the Su-Schrieffer-Heeger model. And the low energy physics is completely dominated by this A1 and the Bn at the 2 ends of this chain. So they will remain degenerate at the 0 energy. All other orbitals will form bonding and anti-bonding state to push themselves away by at least hundreds of millieV. And more interestingly, these 2 electrons talk to each other very indirectly. So the dispersion becomes something like energy proportional to momentum to the nth order, where n is the layer number. If n equals 1, you get the famous linear Dirac cone, which has nothing to do with flat band or correlation at all. However, when you crank up the layer number to 2, 3, 4, 5, very quickly, you start to get bands that looks pretty flat, right? 4 layer, 5 layer. If you put a parabolic band here, you'll find that although it's not parabolic band at all in graphene, but you'll get something like an effective mass of buried electron mass when you get to 5 layer. So you sort of get flat band in crystalline form of graphene for free. There's no twisting, there's no Moiré engineering, there's not even gating. You get flat band. On the other hand, this structure has another advantage, which is since A1 and Bn are located at different layers, you can break their symmetry by applying a gate displacement field. You put them at different electrostatic potential, and that potential difference translates into a band gap opened at close to 0 energy. By doing that, you can further squeeze the bottom of the conduction band and increase the density states there to make it's what I call gate-induced flat band. Okay? So it is a system that has highly tunable, gate-tunable flat band, which is good for correlation. On the other hand, these band crossing points are topological objects. So if you have a monolayer graphene, you'll get the Berry phase pi per valley per spin. But if you go to 5 layer in the rhombohedral stacking order, you get 5 times of that, 5 pi. That's when you have the pristine form. Well, when you open up the band gap by applying a gate displacement field, you get a barrier curvature distributed around the band edge, both conduction and valence band. And here's how it works. Okay, in the momentum space, graphene has these 2 equivalent valley called K and K prime at the corner of the Brillouin zone. And they are time reversal pairs of each other. So in order to preserve the time reversal symmetry, the barrier curvature of the same state in the K and K prime valley should carry opposite sign. So when they are equally populated, it's topologically trivial. There's no anomalous Hall signal or Chern number you can measure. However, as you can imagine, when we have this flat band, as I was showing you the previous page, this degeneracy between different valley may be lifted. And then you can break the degeneracy. You can pick up some finite barrier curvature integration or a Chern number to make the system topological. Okay, so this is a very nice system to explore correlation topology. And before us, actually, Feng has explored the 3-layer version. in like 2019, 2020, where he discovered by tuning the gate voltage of a trilayer, ABC trilayer graphene, HBM Moiré superlattice, you can get multi-insulator, superconductivity, and churn insulators. And at the beginning of my time at Berkeley, at the MIT, we actually collaborated on this ABC trilayer graphene. I was trying to use infrared spectroscopy to better understand the electron correlation effect in the trilayer case. And since then, we decided to go a little bit beyond the trilayer because we think having more flat dispersion may give us something that does not exist in bilayer or trilayer. And we make devices based on first like 5-layer rhombohedral graphene, or A, B, C, A, B. And we make this kind of Hall bar structure where we can measure the longitudinal resistance and transverse resistance at the same time. And we can tune the top and the bottom gate voltage, really just like capacitors, to control two physical quantities. One is the charge density in my system through the field effect. And the other is the vertical displacement field that I can use to open up band gap and control the band structure. These are really powerful knobs that I can play with. I make one sample, but by dialing top and bottom gate voltages, I literally can generate many, many samples that I can grow previously in furnace and compare their property in a very clean way because it happened in the same sample. So the rest of my talk is all about measuring resistance, longitudinal and transverse resistance. For example, you can plot the longitudinal resistance as a function of charge density and displacement field. And you got this very complicated pattern from pentalayer rhombohedral graphene. Okay? There's no Moiré effect. There's no twisting, just crystal graphene. So I can point to you a couple of things. Number one, at the 0 displacement field and the 0 charge density, you would expect a very good metal because there's a lot of densive states. Remember the tight banding calculation of the band structure? However, experimentally, you get a very good insulator here. And that already tells you that without any gating, just a pristine form of 5-layer rhombohedral graphene is showing correlation effect because the band gap is spontaneously generated due to this flat band. When you dope charge into it, of course, like electron dope or hole dope, you get all kinds of funny shapes, like a ring here, some bubble shape, some boundaries. And those correspond to what happens when you have electron or hole in the system, you have Fermi surface. And the correlation effect can do something interesting to the Fermi surface in the flat band case. And you can determine the property of the Fermi surface at these positions by doing two things. Number one, you can apply magnetic field perpendicular to graphene and measure the quantum oscillation. Use that to tell what is the degeneracy of spin and valley at the Fermi surface. Okay? For example, if nothing interesting happens, you get two quantum oscillation features separated by a large charge density here that correspond to every lambda level you fill, you have to fill 4 copies of that because there's a degeneracy of 2 coming from the spin and degeneracy of 2 coming from the valley. And this is what I would call full metal. However, when you have flat band effect, this exchange interaction can spontaneously lift some of these degeneracies, making it a half metal, for example, which means 2 out of the 4 copies is occupied the Fermi surface, or make it a quarter metal, which means just 1 out of the 4 spin valley degeneracy is there at Fermi surface. Okay? This tells you the degeneracy at the Fermi surface, but doesn't tell you whether it's the spin or the valley degeneracy is lifted. In order to differentiate that, you have to look at the quantum geometric effect. For example, you can measure the anomalous Hall effect to tell if the valley degeneracy is broken. Remember, K and K prime are time reversal pair of each other. If they are both populated, you get 0 anomalous Hall at the 0 magnetic field. And related to the anomalous Hall signal, you also get the orbital magnetism, right? You can think of your wave packet is kind of rotating around the center of itself. K is rotating clockwise, K prime is rotating counterclockwise. They will cancel if time-related symmetry is respected. But when you have flat band, this degeneracy can be spontaneously lifted and make it a net orbital magnetic system. So here I'm showing you some example that, for example, if you have a spin polarized half metal, which means you only have spin up, but both K and K prime are polarized, then you measure zero anomalous Hall resistance. If you scan magnetic field, you only measure this linear line correspond to the normal Hall resistance. And that corresponds to 2 out of the 4 copies with opposite valley polarization are occupied. But if you get something like a quarter metal, where only 1 out of the 4 is occupied, you collect the barrier curvature integration from that valley, and that will give you this jump in the Hall resistance versus magnetic field, correspond to the anomalous Hall, integration of barrier curvature, and the orbital magnetism. Okay? So with those background material prepared, now let me show you what we can get with precisely quantized values in the microscopic transport property. Okay? First, I'm going to start with this integer quantum anomalous Hall effect. We all know that when you apply magnetic field to a 2-dimensional electron gas, you can generate the Landau levels, which is perfectly flat, and you get integer quantum Hall effect, where Rxy is quantized at h over e squared divided by some integer. Haldane, in like late 1980s, proposed a scheme to get this effect at 0 magnetic field. To realize that, you have to work at the atomic scales and ask these electron hoppings between different sites to follow a specific pattern. And experimentally, it was first demonstrated in 2013 in magnetic topological insulator system, where you can have a quantized Rxy at h over e squared, corresponding to a Chern number equals 1, when you go to very low temperature and fine-tune the material composition. And later, this similar effect were observed in other material systems like MBT and several 2-dimensional Moiré superlattices. What we did is to avoid the Moiré effect, okay? Just 5-layer graphene in the rhombohedral stacking order. And we approximate it by this WS2, which is a 2-dimensional semiconductor material that has strong spin-optic coupling. So we're borrowing some spin-optic coupling from the WS2 into the rhombohedral graphene, and graphene has otherwise very weak spin-optic coupling. And we play this trick of tuning the top and the bottom gate voltage again. We measure the longitudinal resistance and transverse resistance. As a result, you can see at the 0 magnetic field, there's part of the phase diagram here shows large anomalous Hall signal that's on the order of 5 kilo ohm. And if you park there and scan the magnetic field, you're going to get hysteresis like this, where the 2 states connected by the hysteresis at the lowest temperature have Rxy precisely quantized at h over 5 e squared. So this is like the quantum Hall, but at the 0 magnetic field. At the same time, we get a very big Chern number that equals 5. And this is simply because we're dealing with 5-layer, and there's a barrier phase of 5 pi per valley per spin, and we got a Chern number equals 5. Okay. For people who's interested in detail exactly how this works, let me give you a quick explanation of how to think about it. Okay. As I was telling you, at 0 displacement field and 0 charge density, the sample is an insulator instead of a metal. That's because the flat band already opened up band gap due to correlation. And turns out that state is likely to be in this so-called layer antiferromagnetic state, where the spin degeneracy has been spontaneously lifted, where both K and the K prime valley spin up electron occupy the topmost layer of graphene, while the downspin versions are occupying the bottom layer. Well, that's not enough to give you a net Chern number because you still respect the valley symmetry, right? the two values are time inversely pair of each other, the total Chern number of the system is still 0. It's not topological. What you can do is to borrow this Ising type spin-optical coupling from WS2 to further break the valley degeneracy. And with tuning of the displacement field, you can massage the band structure to realize such a configuration where the K prime valley band is inverted, top and bottom layer polarization is inverted, and also the Chern number is inverted. As a result, the two values no longer cancel. They will add up to give you a Chern number 5. And that's how we can get this Chern number equals 5 integer quantum anomalous Hall effect. Okay? So in this example, we're mostly relying on the correlation effect at the close to 0 displacement field and borrow some spin-optical coupling from WS2. Okay? That's the integer version. Next, I'm going to show you how we can get the fractional version of this similar effect where Rxy is quantized at h over e squared divided by some fractional number. Okay? A little recap of fractional quantum Hall effect. This is high magnetic field. You have a high quality two-dimensional electron gas, for example, in the gallium arsenide heterostructure. At very low temperature, you not only get this integer quantized value of Rxy at the integer filling factor of the Landau levels. When you have fractional fillings of the Landau levels, you also get plateaus corresponding to h over e squared divided by the fractional filling factor of the Landau level. This is known as fractional quantum Hall effect. It's a nice demonstration of what you can get by combining electron correlation and topology. And once you have such a ground state, you have a lot of amazing things that seems to be hard to think about, right? Where electrons become fractions of themselves due to the interaction. And this excitation follows fractional statistics. And you can also get so-called composite fermion close to half filling of the Landau levels. Well, this all requires high magnetic field. Just like people were thinking about how you can realize integer quantum Hall effect at the 0 magnetic field, theorists were also considering how you can realize this fractional version, fractional physics, without using a high magnetic field. There are several discussions about what it takes to generate this so-called fractional quantum anomalous Hall effect, means at the 0 magnetic field. And you can think of their conclusions that you should just mimic Landau levels, okay? Because it worked once there. And if I can mimic every aspect of what the Landau level gives me, maybe I can have a chance to get the same physics. Landau levels are perfectly flat, so you want to have some flat band that has flat dispersion across the whole Brown zone. Landau levels are topological, so you want your flat band not only being flat, but also be with some finite Chern number. And Landau levels are well separated from each other by the so-called cyclotron energy. So you probably want the exchange interaction here to separate the two degenerate topological flat band by an exchange gap. And hopefully, these are enough to mimic what happens in gallium arsenide at the high magnetic field and give you the fractional ground state. Well, experimentally, this is what we did, okay? We're still playing with this 5-layer rhombohedral graphene. And this time, we get rid of the TMD. We don't need spin-optical coupling. But we introduce a Moiré superlattice between the topmost layer of graphene and the top HBN. In this particular case, we got a Moiré wavelength of about 12 nanometer. And the twisting angle is almost 0 degree. This period is mostly due to the lattice mismatch between graphene and HBN. Okay? And we applied displacement field, we open up the band gap, and we put charges at the bottom of this conduction band where the dispersion is really, really flat. Spatially, these charges are located at this layer here, which is the upside of the Moiré. Okay? The Moiré is here, while the electrons are 5 layers away from it. I'll get back to that later. But experimentally, in such a setting, what we found is that if you crank up the displacement field, you measure a region that is very bizarre in both longitudinal and transverse resistance. Overall, it's a tilted stripe in the charge density and displacement field map. While the lower density half of the stripe seems to be very, very insulating over a big charge density range. Okay, so we think this may be the so-called Wigner crystal formed due to electron repulsion, but we're not sure because we're not imaging it. While the higher density part of this stripe seems to have a lot of anomalous Hall signal. This is taken as zero magnetic field. Not only having anomalous Hall, but there is structures on the map. There is a stripe at filling factor 1, which means 1 electron per Moiré superlattice per 12 nanometer. And there are features at the fractional fillings of Moiré, right? 2/3, 3/5, 2/5. And you can tell these features from both the Hall resistance and the longitudinal resistance maps. So all these tell us that we are probably getting a topological flat band. So the flat band effect breaks the degeneracy between K and K prime, so I get the net anomalous Hall signal. Okay? And taking a closer look, this is at the integer filling, 1 electron per Moiré. The Rxy is perfectly quantized at h/e², while the Rxx is only a few ohm within the noise level. So this is as good as any quantum Hall data you get from two-dimensional electron gas in high magnetic field. More interestingly is what happens at these fractional filling factors of the Moiré superlattice. Last year, we have a total of 6 fractional states. At 2/5, 3/7, 4/9, all these fractions follow the so-called Jane sequence, if you're familiar with it, with odd denominator. And you get quantized the Rxy appearing as plateaus, and you get dips in Rxx, as you would expect for the fractional quantum Hall. At that time, these dips are not very small. The smallest value you get here is probably like 7 kilo ohm, which is far from 0, and that's not ideal. But clearly, we have observed the fractional quantum anomalous Hall effect at the zero magnetic field in this setting. Now I can tell you that with some better sample, we're actually able to get to lower electronic temperature with filtering. And if we measure it again, this time at a nominal temperature of 10 millikelvin, while the electronic temperature is probably something like 30 millikelvin, we got a total of 8 fractions. Okay, in addition to the 6 I was showing you, there's 5 9s and 5 11s. And the good news is that the residue of Rxx corresponding to this plateaus in Rxy now become much lower. The lowest we can get is probably like 500 ohm, which is more than 1 magnitude smaller, much closer to 0. And this clearly tells us, well, there's nothing wrong with the physics of the anomalous version of fractional quantum Hall. It should be as good as fractional quantum Hall if you improve the sample quality. We hope with the effort from the community, very quickly we can get it to very close to 0 as what fractional quantum Hall in very high quality gallium arsenide shows. And the quantization of this Rxy is also very good. It's like limited by our noise in measurement. The value of Rxy is within 0.1% of the expected value for all these fractions. So everything is moving in the right direction. And since then, this fractional quantum anomalous Hall effect has been observed in 6-layer graphene, 4-layer graphene, and we have further development that you're welcome to check if you're interested. So experimentally, it is satisfying that we observe this effect. However, I should tell you that we don't understand why and how we can get fractional quantum anomalous Hall effect here. You may get confused, right? Because I'm motivated by telling you we should mimic Landau levels. Well, in reality, that just doesn't work here. For 2 reasons. Number 1, we do have a very flat bottom of the conduction band. But as I was telling you, when we observe this effect, the electrons at the flat band are residing at the side opposite from where the Moiré superlattice is. So how do they even know there is a Moiré superlattice? How do they even feel the Moiré potential and adjust themselves to the Moiré potential? This is not clear. Well, maybe you think somehow there's buckling of the structure, so these electrons can indirectly feel the Moiré effect, even bigger trouble is waiting for you, okay? You can fold your band structure into the Moiré mini-Boron zone, just like how the Cronish panning model works. You got the mini-Boron zone, you fold your band structure into it, and if you really do that, even with a weak Moiré potential, you don't get an isolated flat band like what you get in the lambda level case. The first flat band is overlapping with the second or even the third Moiré band in energy. And this doesn't look like a lambda level separated from other lambda levels by cyclotron energy at all. So nobody understands what's going on here and how you can get fractional quantum anomalous Hall effect in this setting. Even as we're speaking today, there are a lot of theoretical discussions, including Michael Zalatel here, local. Nobody knows what's going on. There's no consensus. The only consensus is this is beyond the lambda level picture, and we should understand it better. And you may be aware of the other material that was discovered last year in the same year. We have two systems showing fractional quantum anomalous Hall effect. Well, the other system is twisted MOTE2. That system shows two fractions at that time, and that system is just very different from this Graphene HBM Moiré system in every sense that people think matters. In twisted MOTE2, there's very strong spin-off coupling, and there is the so-called layer pseudo-spin degree of freedom that forms Skyrmion patterns in real space, and there's effectively an emergent magnetic field due to all these. Well, graphene doesn't have any of those. So I think it's valid to ask a question like, do we really understand how to generate this fractional quantum Hall physics at the zero magnetic field? Clearly, the two systems look very differently, but somehow magically they share the same phenomenon where you get fractional quantized RXY. So we're still trying to understand this physics now. Okay? So this is what you get when you approximate the 2D crystal graphene by a Moiré superlattice effect. Okay? In the last, I'm going to show you some, I think, personally, I feel it's even more interesting and an even more simpler setting. Without any proximity effect, without WS2, without spin-off coupling, without Moiré, just pure rhombohedral graphene, we got some very bizarre looking superconductivity that I will share with you. Okay? This time it's 4-layer, it's not 5-layer. Tetralayer rhombohedral graphene, and we do the same trick by applying charge density, gate displacement field, tuning the gate voltages, right? And we measure the longitudinal resistance RXX. As you can see, there are a lot of features on this map, but there are 4 regions that shows RXX vanishing, which I call as SC1, this big oval here, SC2, SC3, and SC4. For every one of them, we have checked that the resistance does go to 0. We checked the nonlinear IV. We checked the, their BKT transitions. We're pretty confident they are all superconducting. Especially these 3 here correspond to when we open up the band gap to generate a very flat bottom of the conduction band. And we put charges into that flat part, okay? Again, there's no Moiré effect. There's no TMD or SOC. This is just what pure carbon does. And the TC of this superconductivity, none of them is high, okay? We're all talking about below 300 millikelvin through the BKT fitting. However, you probably already noticed some very bizarre looking features that, there's a lot of fluctuations in SC1, SC2, and then the neighboring area here. Well, SC3 and SC4 are mostly homogeneous. As far as we can tell, SC3 and SC4 just look normal, that you apply a small outer plane magnetic field, you can easily kill these 2 superconductors. Well, SC1 and SC2 look very fluctuating, and we decide to look into what they are. The first thought came into mind is, okay, you have a lot of fluctuation. Maybe that's because you're scanning the gate voltage You are triggering something by changing the voltage on your source meter, and maybe that caused the sample to be somewhat unstable and give you fluctuations. So the first thing we did is to park inside the SC1 region. We fix the top and the bottom gate voltage and just watch it as a function of time. Surprisingly, we found that this state, for most of the time, stays as zero resistance, or the superconducting state. But from time to time, it will deviate from zero shortly, or stay a little bit before go back. So this fluctuation that we saw in the previous map is not due to triggered by some gate voltage scanning. It is a temporal fluctuation. The superconductor itself will just do this, possibly due to some thermal radiation from the environment or coming from the leads. Okay? And the next thing we did is staying at the same state and test its response to magnetic field out of plane. And what we found is that you can actually observe some hysteresis. What do I mean by hysteresis in a zero resistance state? Isn't it always zero resistance? Well, what you actually see is that there are two spikes as you scan magnetic field that deviate from zero, and they don't overlap. You scan forward and backward. There is a clear separation between the two non-superconducting states, and that tells you this is like a magnet. Okay, let me pause a second here. We all know superconductors do not like magnets. If you're in a bulk superconductor, you have the so-called Meissner effect, where the magnetic flux will be expelled by the superconductor. Well, when you go to two dimension, the magnetic flux can penetrate through the 2D layers, right? That's fine. But we're talking about the superconductor not only can get along with magnetic field, but itself behave as a magnetic field, behave as a magnet. Because magnet will fluctuate from pointing upward to downward. A magnet will have hysteresis in response to a scanning magnetic field. So we are talking about a very bizarre superconductor that behaves as a magnet. So when you apply an out-of-plane field, right, say 0.1 Tesla, you get to this saturated regime, you're far above the coercive field. What you find is that instead of being killed, SC1 and SC2 actually got stabilized. All the fluctuations that we were talking about are simply gone. The magnetic field help the superconductor to be stabilized. And that also agrees with what you would expect for a magnet. Okay? And there are further analysis we can do. As I was telling you, you can do quantum oscillation measurement to figure out the degeneracy at the Fermi surface. And you find that in this big region here, neighboring the superconductor, we got so-called quarter matter, which means 1 out of the 4 spin valley degeneracy is occupied. And that agrees with what we expect from the flat band and correlation effect. On the other hand, this neighboring state here also has anomalous Hall signal, and that immediately tells you it is valley-polarized. And you have this hysteresis, okay? Orbital magnetic. So that tells you at least this neighboring state here, we should think of it as a spin and a valley-polarized quarter metal. Okay? And this is above TC. You see this dashed line here outlines the SC1 I was showing you. And interestingly, even above TC at 480 millikelvin, you have anomalous Hall signals inside this big oval here, both inside and outside. Okay? So the star and the square positions are both inside SC1. When you scan out-of-plane magnetic field, you get this jump in RxY, and you get a hysteresis loop. And this is absent from any other superconductors, as far as I can tell, from literature. And when you cool down the temperature and park the sample at the star position, which is inside the SC1 region, you find that from this behavior, you get the slope corresponding to the normal Hall plus this anomalous Hall due to valley polarization. When you cool down, eventually both of them will go to 0, because when you get into the superconducting state, it just gets shorted, right? Rxy becomes 0. But you still have these spikes when it, when the superconductor, is switched by the external magnetic field from polarized in the K valley to polarized in the K prime valley. And this is basically the spikes you were seeing in the RXX scanning inside the superconducting state. Okay? And there's another very unusual feature. If you apply autoplane magnetic field, you can ask, like, how high a magnetic field I would need to eventually kill the superconductor, let's say SC1. Because eventually you have to kill it, due to orbital effect, right? This is the autoplane magnetic field. And it turns out the critical field is almost 1 Tesla, which is a crazily high number for some superconductor that has a TC of only 200 millikelvin. So based on that critical magnetic field, you can sort of extract a coherence length based on the calculation of the magnetic flux. You get something on the order of like 20 nanometer. Okay, you can think that's how big your Cooper pair is. And you can also plot the inter-electron distance at the given charge density, right? That's this dashed line here. And you find that in SC1, they are already pretty close to each other. So this is telling us that we're sort of close to the so-called BEC to BCS crossover, although we're safely in the BCS side, but we're very close to it. And this may be suggesting that we have strongly coupled superconductor. So let me summarize what I've shown you in this superconductor part. Phenomenologically, we got RxX fluctuation and hysteresis in the superconducting state, and this is absent from all other superconductors. And even above TC, it has anomalous Rxy and hysteresis. This is again absent from all other superconductors. And if you believe this superconductor is stemming from a spin and valley-polarized parent state, that has several implications. Number one, so it's valley and spin polarized superconductor, and both electrons come from the same valley, which means your Cooper pair has a big momentum, like in the FFO picture. And you choose one of the valley, right? And that means you spontaneously break the time reversal symmetry. And this is, Chiral superconductor. The time reversal symmetry is broken at the orbital level. This is not the so-called ferromagnetic superconductors, where spin spontaneously order, and that doesn't have to be chiral. That could be just a px or py, right? So we think this is rather unique, that it is a time reversal symmetry at the orbital level, a superconductor. What is unclear is this a topological chiral superconductor or not, or chiral topological superconductor or not? Is a pairing symmetry just px or py, or it is px plus minus ipy? That is not known. And we have no idea what the pairing mechanism is at this moment by just doing DC transport. But I'd like to remind you that this is in possibly the simplest setting, just layers of carbon in the crystalline form, no twist, no Moiré, no spin-off coupling. It is giving us this very exotic superconductivity phenomenon. Okay? And let me see. Maybe just a couple more words on like the chiral superconductivity, okay? Because the spin and the valley are both polarized, it's a single flavor superconductivity. Let's say you are in the P wave channel. It could be px or py or px plus minus ipy. So theorists has been telling me that, look, if you're already valley polarized, then you have this time reversal symmetry already broken at the atomic scale, atomic lattice scale, because that's what valley determines. You have this winding, in one way, right, by occupying just one valley. And basically, your superconductor is valley polarized. It breaks the time reversal symmetry. It breaks the inversion symmetry. But it preserves the PT symmetry because you just swap K and K prime twice. Well, you can think that, okay, if my time reversal symmetry is already broken at the atomic lattice scale, it will probably couple to the other parameter, which happens at the coherence length scale or the size of the Cooper pair. So maybe it will automatically make my other parameters to be px plus IPY or px minus IPY. Right? K value and K prime value, one of them choose px plus IPY, the other choose px minus IPY through this coupling. And if that's indeed the case, this should be a topological chiral superconductor. But we're far from claiming that. Yes?
Is your Fermi surface angular? Does it have two Fermi surfaces?
Very good question. Maybe one of the, maybe SC2 is an annular Fermi surface. But SC1 can still be a single pocket. No, we don't know. Because the band is too flat, you don't have quantum oscillation signal there until you ramp up to something like 3 Tesla. But 3 Tesla may be too high a number to keep the sample in the same state, right? So I'm telling you what is the fermiology at the Fermi surface at this moment, because we just don't have quantum oscillation at exactly where we observe superconductivity. Okay? And there have been already several theoretical works considering the superconductivity in this system. Okay? Just a simple flat band, no twisting, no Moiré, no SOC, and seems that theorists are more confident than I am on claiming this has to be a topological superconductor. But anyway, just to show you, people are working on this. So I have shown you the physics that we can get out of this simple carbon in the crystalline form. No twisting, no Moiré, but with some extra ingredient coming from proximity effect. And we have already observed many interesting phenomena that here I use blue characters to label. And there are other interesting possibilities we are still investigating. But we think this is a nice platform we can build upon to get emergent quantum phenomena. And with that, I'd like to thank you. Yes.
So you measure the resistance as a function of time, and you see that basically there are time periods where the resistance is like a flat constant that is finite.
Yes.
So if I think of the sample as some kind of magnet, what is that state related to? What is that state, like what's the form of that state?
What's a what?
Because when you have a magnet, no matter where you point it, if it's superconducting, I would imagine the resistance is always zero.
Okay, very, very good question. We think what's going on is that maybe you have a domain wall stuck in there that's cutting through the pathway from source to drain electrode, and that could give you a non-zero resistance. So this is like microscopic dynamics, and we're not able to claim that, but this is just DC transport, right? And there are, having domains polarized in different values is not uncommon in such kind of graphene system, in both twisted and untwisted graphene.
Okay, so you are saying basically a domain wall is not superconducting.
A domain wall, could have a resistance, right? Especially if one domain is polarized in K value, the other is K prime value, tunneling through, probably cost you some, cost, right? Momentum mismatch thing. And one thing I can tell you is that if you warm up the sample to the normal state or use magnetic field to kill the superconductor, the normal state resistance is on the order of 2 kilo ohm. While the spikes we're talking about here are much smaller than that. So this clearly tells you when you have a non-zero resistance, it's definitely not the whole thing becomes non-superconducting. And that's aligned with the picture that maybe there's some domain structures in there. Yes, Mike.
Do you see those spikes, the rate of them change as you heat it up? Does it follow any Arrhenius behavior?
Okay, I wish I can tell you yes. But the dynamics is actually very complicated. It depends on how you cool it down, and depends on how long you have been staying there. I think in general, if you stay there for a week or so, maybe everything in the dew fridge settle down, its fluctuation becomes less frequent. And it also probably depends on how you train. Maybe if you do a field cool down, you get less domains, and this becomes less frequent. So the absolute time scale of this fluctuation is a bit hard to gauge and tell now. But one thing I can tell you is that there's not only fluctuation in the superconducting state, but this is the quantum metal, right? This is the quantum metal state, and quantum metal also fluctuate. The rate of fluctuation in the superconductor and the rate of fluctuation in the quantum metal, no matter how absolutely the time scale changes, but these two rates are always tied. In other words, the understanding of this neighboring quantum metal state give us a lot of confidence in interpreting what's going on in the superconducting state.
Any other questions?
Yeah.
Have you tried to do any measurement of the superconducting gap? Region?
No, this is just DC transport. And there's no junction yet.
I think that's also important for, to see the, verify the superconductivity.
I agree with you. This is the first glance.
Any further questions?
Yes.
If you have a stripe, as John was suggesting, is it possible that measure X-rays?
What defines it?
X-ray defines a stripe that would be short circuited, as John was.
Oh, you mean some cosmic ray coming in and temporarily perturb the sample?
No, I was wondering if you had a short circuit, as two people in the past had mentioned, I should have read it right after you said it, but I'm wondering if you could tell that. You said that there might be some sort of short circuiting happens.
No, I'm not saying this short circuiting. Yeah, I mean, when you deviate from zero resistance, I think there's probably a domain wall lying in the sample.
No, I see.
Yeah.
Could you find that out with other methods?
Oh, of course. If you can image it spatially, you may be able to capture these domains and domain walls. Yeah.
Okay, let's thank Long again.